Okay, welcome. My name is Tim O'Brien, and I'm here with Ori Hernstadt. We're with a company that is named Akiban. It's based in Boston. I live in Chicago, so we're not working on much sleep. And right now, I'm going to introduce Ori. There's a library called Persistit, and Persistit is an in-process storage engine. And I think it's probably going to be as important as BerkeleyDB, but it's got some differences to it. And so one of the things I wanted to do is set the stage. When I came to Akiban to help him work on Persistit, one of the things that I noticed is that they wanted to do this as an AGPL licensed library. And I said to him, the Java community adds dependencies using either Maven or Gradle or something like Ivy. And if you make your library AGPL, not a lot of Java people are going to want to add that into their project. So the Persistit library has been re-released under the Eclipse public library. So I think that makes it even easier to use. It's going to be freer. And I wanted to give him the chance to introduce it to all of you because it's the foundation of the Akiban database. So it's all you.
I think it's all me. Can you hear me? Are you guys enjoying the conference? I see a few nods. So we wanted to start out by giving you a sense of what Akiban does in under 30 seconds. We'll fail at that, but we'll try to stay close to that. And then dive right into Persistit in as much detail as 30 minutes will allow. So Akiban comes from frustration with mostly relational databases that make it very, very difficult to handle objects, actually, or to run queries, if anybody has witnessed that. And for me personally, it came from an experience of trying to work with highly complex objects. We used ORMs like Hibernate and others. And we realized that while designing objects, they exploded into a lot of different tables. And that the performance, both of accessing objects and then querying on top of this data in a relational database with all these tables became very, very bad. So we started looking at it again. This is back at in Boston. We started out at MIT. And we wanted a solution that, on the one hand, embraces objects. On the other, allows you to take the full power of SQL. And that's what Akiban does. That's our day job. So if you think about an object like a JSON document that has information about a user, and the user has orders, and he has items, and he probably has address, and visits he made, and preferences that he has, and friends that he has, and a bunch of different things. Our natural mode of thinking about it is, let's think about this as an object, as a document. And that's exactly how we think about it at Akiban. The only difference is we start saying, okay, we're going to take every level of that object and consider it a row, but compose these rows together. So we'll store that user row and that order row and the item rows and the next order row, etc., as independent rows, but we'll co-locate them. We'll keep them together in the same space. And what it does is it brings something pretty interesting. It gives you the ability to look at the data in two ways at the same time. It gives you the ability to look at data as an object, because it's just an object, but also to look at it through SQL, through the lens of tables, though they're not separate. The data is not separate. So if you look at it through the lens of SQL, and this is an attempt to do just that, if we have the same users and orders and line items, those would be three different independent tables. What we do in Akiban, we keep those as independent tables logically, but physically, we look at exactly the same co-located rows as the document. So this is literally what we do if we look at the data through the lens of a table, and we create tables and put rows in them, we'll make sure that this data is co-located. And so what the system, if we continue, there we go. So from a logical perspective, we expose JSON or objects as a logical perspective, or SQL as a logical perspective. But under the hood, there's a single unified data structure, this collection of rows. And beyond being able to access the objects, obviously, we realized that we can actually start running SQL a lot more efficiently than we could until today. And the reason is we don't have to do the joins that we traditionally need to do to bring the related information together. I'm not going to spend a lot more time, but to say that the way we actually expose the system, and I try to keep it very technical, is we can consume JSON or tabular data, expose it in exactly the same ways. And one other thing we realized that we can do is we can sit alongside existing systems, like MySQL or Postgres or even Mongo now, and consume their data and expose it in this variety of formats. But obviously, the bigger goal is to give a unified view, finally bridging objects and relational and bring them closer together. So that's what we do at Akiben. But of course, there's the night job. And to get this to work, we needed a storage layer that could support co-locating this data in this way, that was flexible enough and strong enough and transactional enough to give us the capabilities that we needed. So
if you think about what this database does, it gives you two views of data. But right now, the question for all of you is, should I use Mongo or should I use a NoSQL database? And you're likely saying, well, we need to use a document-oriented database. Well, what they've done is they've created a database that lets you query things as SQL. You can view it as a traditional relational schema, but then you can turn around and grab things as JSON. And now they haven't done it by writing a layer that just adapts a relational database to JSON. What they've done is they've changed the underlying way that they store data. And that's really what this talk is about. Persistit is a fundamental change to the way a relational database can store its data. So what is Persistit? This is the core of the database. And it's important to emphasize that we're not talking about the database. This is not the emphasis of the talk. We're talking about the library that enables this hierarchical approach to what they call table groups. So Persistit is a open source, it's Eclipse public license, transactional. So this thing supports high levels of transactional interaction. It's Java-based, it's 100% Java. So unlike BerkeleyDB, which also has a Java version, this thing is starting out as a Java storage engine. It's a B+Tree library. I'll let him talk about the nuanced differences between B-trees and B+trees in just a minute. So it provides this fast, highly concurrent, direct data access with full ACID compliance. This is my thing. So I sort of grew up on Java. My main interest for the last decade has been centered on Apache licensed components. I really do think that it's important for the Java community to lead with a license that's business friendly, that has weak copyleft. I think the Eclipse public license is that. I think everybody in this room would be comfortable integrating the Eclipse public license into whatever project they're working on. More importantly for me, it's on that list. I think it's category B of licenses in the Apache Software Foundation that can be incorporated as binary code into a software distribution. So while he has a database that he's going to try to move, I'm more interested in people using this in their open source projects. And this is our announcement that this is covered under a license that will allow you to, you can just put this in your Maven POM. You can put it in your Gradle build, and you won't have to open source all of your code. So right now, how is this thing being used? We have had limited interest, but mostly because we haven't put a lot of publicity behind it yet. This is our first big announcement. So we've had people show up. They're replacing an H2 database with Persistit from JRuby. It's a quote. It's very easy to use from JRuby. There are some examples that we've fashioned up. I wrote an example. It's on GitHub. You can go check it out. What we've done is we've parsed some data from Freebase. Freebase is this open source collection of data. And so you can see within, a couple of hundred microseconds, maybe I think 600 microseconds, we can locate records in this in-memory database. And there's another example that uses the Akiben server called Mapper. And Mapper parses the public Twitter stream and then draws tweets on a map. And you can see that what they've done in the database is they've used Persistit together with a z-order index for geospatial that allows you to get nearest neighbor searches in fractions of a second. I think it's 4 or 5 milliseconds at this point. Could probably be faster. Another major use case is someone wrote to our support email that they are tracking, 500 million log messages. Each message is about 70 bytes. And I believe that the use case was from COBOL. And they're using Persistit as a replacement for some legacy database that they used. One thing that he said in his email, he was attracted to how easy it was to use and the license. I'm a licensing nut. I think it's important that this be open source and free. So there's a lot of things you can do in Persistit that you could do in another NoSQL database. You could do it in a traditional relational database. But one of the things that we're seeing is that the very concept of memory is changing on us right now. So there are some test machines that he's had the luxury of using that have 2 terabytes of memory. There's non-volatile RAM that's about to hit. Maybe some of you know about this. This is going to change the way that we view data. And if you can store data in these specialized storage engines, and if you can fit it all in memory, we're talking about things that you might be impressed if they take 4 milliseconds, taking 4 microseconds, 40 microseconds. This is the sort of level that we're working at, and this is what they're designing their database to handle. So I'm going to pass it back to Ori. He's going to talk about some of the specifics with Persistit, some of the concepts, and how you can start using it. Take it away.
Thanks, Tim. So I'd like to put you guys in my shoes, which are actually probably too small, but think about where you stand when you think about building a new structure, a new database from the ground up. What we wanted is to progress pretty rapidly. We had experience with Java before, and we thought that that was the right approach for us. We realized that from experience that databases don't consume time processing CPU. Of course, that's a big amount of the time, but really it's about moving data. And it's not anymore moving data from disk to memory. It's about moving data between the different layers of memory, from the DRAM to L2 to L1 to the CPU itself. That's where time goes. And especially when you start considering a scalable distributed system, that becomes even more pronounced. Most of your data is in memory, and the ability to move fast is really important. So we picked Java, and the architect behind Persistit, who's an incredible guy, his name is Peter, has thought deeply about how to actually construct it. And the main components that I'm going to talk about today are volumes and trees. That's where you see those triangles. And a volume is, in the simplest form, literally a file. It could also be a virtual file that spreads multiple machines. Within a volume, we have trees. And trees are B+Trees, a unique variation of them. But what are B+ or B trees? Anybody in the room? Hands? So B+Trees, I'm seeing a few hands, hesitant. B trees generally are a way to order keys and values. So they're just a key value store. But the difference is that this key value store organizes them in an ordered way, as opposed to a key value store that it just hashes them around. And that is critical for a database system that wants to support range operations. Range operations like, give me all the people who are between the age of 26 and 28. That's a range, and I'll need to scan and index. So that's exactly what these trees actually allow you to do. And we'll talk about the interfaces to them in a second. Oh, not yet. The other big part of Persistit is the buffer management. Persistit manages its own buffers, and I'll talk a little bit about why that is, but it literally does not leave anything to happen chance. So what goes into the buffers, how they're evicted, how they're managed is all done internally. There are two main interfaces into Persistit. One is Exchange. Exchange is a way to exchange information. Here's a key, give me the value. Here's a key and a value, please store them for me. And the other is transactions. Transaction, if you will, encompass operations that happen through exchanges. So sounds pretty simple, and it is actually pretty simple. I'm going to start walking through the operations that you can actually do. So the main objects are keys. So what is a key? Well, key could be a customer ID, a social security number, a name, whatever it is that you want it to be. And really, keys are very, very flexible in Persistit. But there's a little magic to them, which is hiding behind this segmented, the word up there. And what segmented means is that you can take a key and you can construct it from multiple parts. So you may be wondering why that is important. It's important for the Akiban server because that is the way that we compose rows of relational data together. What does that mean? If I have a customer and his ID is 20, and then he has, so I'll put it customer 20, and then his row. Then I want his orders, right? He has order 1, order 15, order 20. We'll compose the keys for those orders as customer 20, order 1, and then the value. Customer 20, order 15, and then the value, the row of the order. So it allows us, by using these very flexible keys, to co-locate related data. It's actually a pretty convenient mechanism. What we've seen people outside of Akiban do with it is construct pretty sophisticated indexes. So for example, if you want an index that has first name, last name, birth date as part of a single index, you can do it in Persistit. And the API, the way you interact with the key, is exactly that. We'll see that in a second. The second important object is a value. It's a bit simpler than keys, but it also has the same kind of mechanism. You can append to a value, you can detract from a value, you can actually put a whole object, and Persistit will serialize it very effectively into one of these values. Above both of them is the exchange, which provides an interface to a tree. So you open an exchange against a volume and a tree, and that exchange handles the communication of data back and forth. It's a very lightweight mechanism, and for us it's been a very, very effective mechanism. And you'll see a little bit in the examples how flexible this can be. Oh, we went to the example? No transactions yet? Sure. So how do you use Persistit? We'll show Maven and a bunch of different ways that you can get it, but it's literally whichever way you get it. It's a jar. To use it, you just initialize it. You can see here two utility functions that we just put for clarity: get exchange and get transaction. You see that an exchange is opened with a tree within a volume. And a transaction is just stating I want to begin a transaction. I haven't even stated what it is operating on. And here are some methods that we can invoke. Exchange load. So let's load 10 values with keys going from 1 to 10 and values going from value 1 to value 10. Pretty sophisticated as an example, I know, but probably gives you the sense. So we use that utility get exchange, iterate, and here you start seeing what the exchange allows you to do. To get a key, clear it, and append a value to it. So I cleared it, and now I put a number in it, and then I'm getting a value, the value for that key, clearing it, and putting value underscore the number. And now I'm storing it. Sorry. One before? There we go. So to traverse it, you literally traverse it like you would any collection. Transactions. Transactions are, oh, we have time. Transactions are a science to itself. The main idea behind it is that you don't need to see, or you will not see what other people are doing to the data until their data is committed. I will talk a little bit more in depth about transactions, but for this example, I just wanted to show how you can compose a transaction and then put whichever operations you want within it, and then commit or roll back that same transaction. So we get a transaction from our utility, begin, do an exchange load, so load and iterate over data, do whatever you want with the data, and then commit, and then that's basically it to get started. The transaction mechanism is actually quite powerful. We've extended it significantly pretty recently, and it's very, very efficient, and I'll talk about it in more detail.
Okay, so I think you should probably be the one to explain a Lehman Yao B-link tree, because I don't think I could.
I should, but I think everybody will.
So the person who invented this, I just want to make this clear, his name is Peter Beeman. And one of the things about this library is that it's been around for years, right? It's been in existence for multiple years. When I got to Akiban, it was not open source. They wanted to release it under the AGPL. I said, don't do that. That's not necessarily the kind of open source you want. And it's been in production. I probably can't say what customers are using it in production. Maybe you can and should. But the point about this thing is that it's fast, and that if you look at the code behind it, we're using like, bit level manipulation to make sure that, all of the data is being, very quickly stored. So one of the things about the concurrency that's impressive is that we don't have the tests out yet, but I think Peter mentioned that we've got like 100,000 simultaneous threads. That's the level of testing that he has done privately. But I think that we're just at the beginning. We're going to see people use this in ways that we can't anticipate, and that's the point, right? A lot of startups would say, we have a database, we want to protect it, we want to protect the IP, we want to hold on to this is our secret advantage. Akiban's strategy now is we're open sourcing the basis of this database. So we want you to use it, we want you to take it, incorporate it into your own databases, into your own projects. So I'm going to let you talk a little bit about the hybrid logging and journaling.
So honestly, it's been surprising to me how quickly we started getting benefit from open sourcing this. I thought, okay, this is going to be a long process, and then within a week we had a few bugs reported against it, and then we realized that somebody actually heard us and is using it. Like Tim said, what Peter did, Peter is the main architect, the main author of this library. He comes from healthcare. He comes from building a very large-scale medical record systems. And he wanted something that would just scale, that wouldn't hit all the problems that he's seen in the past. So he went to great pain to eliminate almost all of the locking in the system. Beyond that, he went to great length to make the write load very, very efficient. So the way he did that, he implemented a hybrid logging journaling system. So what does that mean? It means that as data gets written to the system, it doesn't get replaced in place within the tree. Instead, there's journals that get filled up. And the number of journal is up to the user. You can set to as many as you want. But we've seen that as we increase the number of journals, each of them, we like to set them to about 1 gigabyte. So as we increase the number of journals, so the number of times that we'd actually have to replace in place decreases significantly. From with 10 journals, we see we get about 8 changes in place for a specific workload, whereas when we increase that to 50 journals, we only end up with 2 changes in place. What we're really trying to do is we're trying to write sequentially, because that is a key idea, not just for SSDs, not just for disks, but also for memory operations. And it's been working pretty well. The other thing, which is, I think on the previous slide, is we eliminated most of the object allocation in the system. And one of the big lessons for us has been to really minimize object allocation, to chart that 20% of the code that is the critical path and leave literally no object allocation in the process. Because while the JVM is a pretty amazing beast, For a database that needs to run without too many hiccups, that was the biggest source of trouble for us. And so we just removed all of the object allocation from there. There's a bunch of other things to say about the transactions, but perhaps the most important one is that they are optimistic. What that means is that we won't keep logs and check every time that somebody does something if it conflicts with something else. Instead, we'll let transactions run their course, and only when they try to commit, if they conflict with another writer, we will wait to see if we have to roll back, if that writer succeeds, or if he doesn't, then this transaction can go forward. And it's been an interesting experiment. It worked out very, very well in terms of performance. So I talked about most of those. I think we'll continue.
Okay, so let me just very briefly talk about some of the alternatives. There's MapDB, which was recently renamed from JDBM. You know, the one thing I like about open source is that this is not competition. This is just another alternative. And Jan Kotek is working on this, and he's investing a lot of time. He's trying to implement a lot of the same features that I think Persistit already has. So if you're looking for alternatives, MapDB is another 100% Java alternative that does similar things, maybe without the hierarchical keys. LevelDB is a C, C++ option. BerkeleyDB is out there. Oracle, I think, owns that license at this point. So the unique differentiators for Persistit are H keys, hierarchical keys, which are showing up all over the place, by the way. There was a new database announced by Google just a few weeks back, which is based on this whole idea of hierarchical schemas. Performance is a differentiator for Persistit. You're about to see that. And full ACID compliant at really high concurrency. So some of these read benchmarks are pretty impressive. And if you want to talk about these, it's up to you.
Well, benchmarks are benchmarks, and they're always in the eye of the beholder. But we have benchmarked internally to see how it actually performs. And we've benchmarked against native alternatives. And it's pretty amazing to see what the JVM can do and how optimized that code can become. Definitely this benchmark against Berkeley is very repeatable. So we put it up on the website if anybody is interested. What you see is that the longer keys, the longer records don't have as much of an advantage as the shorter ones. And the reason is simple. With the longer keys, you're actually transporting more data back and forth. And that it consumes most of the time. When the keys are shorter, you start seeing the efficiency of the code and the access paths into the data that take effect. So you see that with the 10-byte reads, they're a lot more, or the difference is a lot more striking because Persistit almost doesn't suffer any degradation.
So I can actually cover this slide. Mm-hmm. This is our last slide. If you want to get started right now, one of my big things that I pushed for is publish these things into Central. Central is where you get software from. So Persistit is in Central. You don't need to install anything. You can just add it as a dependency. If you have a Gradle build, you can use the code that I've put in there. But we have a minute left, and I just want to try to summarize this. Maybe you don't know this yet, but you're about to have someone ask you, well, what would you do with 2 terabytes of RAM, right? And that's an important question to know the answer to, because the new server architectures that are starting to be looked at by companies like Intel and companies like AMD, the new types of disks and storage, like non-volatile RAM, that are about to hit. You know, storing a 2 terabyte data set in Persistit and coming up with a specialized approach could be the thing that provides you with a competitive advantage versus the competition that might be going with a database. If you don't have to pay for I/O, if you don't have to pay for the network hop, you can look at something like Persistit. And I think that Persistit is positioned to be as important as BerkeleyDB was over the last 10 years. And our time is up. So if you have any questions, come down and ask us, but I think we're done. Thank you.